chance posting this so I can send people invites?
Right, this is, I'm going to do this one from yesterday. This was on yesterday's homework. I did one off of yesterday's homework with you to start off with. This is another one. It's a little bit different than one that we did yesterday, or any of the problems that we did on our notes yesterday, because there's kind of an added piece to it. We have variable in the exponent, which we saw yesterday, but that variable is an expression with multiple variables. And so in the exponent, we have x squared plus 4x. And so what we need to do here, and there's still a couple of different ways that we could solve this, okay? One way is I could rewrite this as a base 3. That would be one way I could do it. You could log it, frog it, solve it. That would be another way you could do it. There's a couple different ways to do this. Now, probably the hard part about rewriting this as a base 3, 27 is a base of 3 or a power of 3. 3 to the third is 27. But what would make it move to the denominator? A negative, okay? So what I could do, and I think this is kind of the easier way to do it if you kind of know some of those exponent rules, is I could rewrite 1 over 27 as 3 to the negative 3 power, okay? And the only reason we would do that is because these both have base 3 now. And I think that's kind of an easier way. If you're not real good with the power rules and things like that, then you could log a frog and solve it, like we did yesterday. And here, the reason why I think that's a little bit easier is because these are both base 3. Now I can just do x squared plus 4x equals negative 3. Because the bases are the same, then the two exponents are the same. And then here's where it gets a little bit different. What we have here is a quadratic equation, okay? And so this goes back a couple of chapters ago, and we've seen it off and on throughout, but we got to solve a quadratic, and we know that our first step in solving a quadratic is to set it equal to 0. And then we can do all kinds of things. We could graph it, we could factor it, we could do the quadratic formula if we really wanted to. I think probably the easiest thing to do here would be to factor it. What multiplies to get 3 and adds to get 4? 3 times 1 is 3, 3 plus 1 is 4. We set both of those equal to 0, and we get x equals negative 1 and x equals negative 3. Okay, and like I said yesterday, it's okay to get a couple of answers on some of these. I know a lot of them that we did yesterday, we only got one answer. What you probably should do, especially when we have negatives, is does this really work? Well, if I plug in negative 1, negative 1 squared is 1, 4 times negative 1 is negative 4, 1 plus negative 4 is negative 3. And what we just said here is 3 raised to the negative 3 is 1 over 27. Okay, so when I get negative 3 as an exponent, it's okay. What we don't want to do is we don't want to, when we said yesterday that sometimes we could have no solution. If I'm taking the log of a negative, we can't have that. But I can have a negative in the exponent. Okay, if I plug in negative 3, negative 3 squared is 9, 4 times negative 3 is negative 12, 9 plus negative 12 is also negative 3. And so both of those give us 3 to the negative 3, which it really is 1 over 27. Okay, so both answers do work. And so that's a situation where we can get two answers, and both answers work. But probably not a bad idea to check to make sure they really do work. Okay, so a little bit added layer because of the factoring or the solving of the quadratic, but getting there is basically the same thing as we did yesterday. I think that's the hardest part about yesterday's lesson, is that a lot of those problems are, they're all a little bit different. Just kind of like, okay, where do I get started kind of thing, like we said yesterday. Okay, today we're on to the last lesson of chapter 5. And in 5-6, what we're going to talk about is kind of like applications of compound interest. And so you're going to see some story problems today. Have some different kinds of scenarios. So when I say applications, applications is kind of where can we apply some of these things that we've been doing. Okay, we've already talked about like money, obviously compound interest. Our compound interest formulas that we've talked about is one way. Today we're going to talk about some different scenarios. We talked about like 5 years ago or 6 years ago when COVID hit and the virus was growing exponentially, right? It wasn't just going by the same amount. It just grew like crazy. And so that's an exponential growth. The number of cases went up really, really fast. I could think of if something is decaying, like you think of a leaf falls off a tree, it's going to eventually decay. So it loses its substance or its material over time, and it's going to lose it exponentially and eventually decay into nothing. There's a formula that we're going to use for a lot of these scenarios for growth or decay. And the formula that we're going to see today that formula sheet that I gave you for the quiz had this extra formula on it. And that's the formula that we're going to be talking about today. And we can use this for either growth or decay. Either one of those would be fine. The K value is going to tell us what kind of exponential growth or decay that we have. If K is positive, positive means there's going to be growth. If K is a negative number, then it's going to be decaying or decreasing over time. Okay, I mentioned like a decay, but like you think about like the price of a car. If you buy a car and it's brand new in 2026, 10 years down the road, the price of that car or the value of that car has decayed or decreased exponentially. Okay, it's not going to go down by like $1,000 a year. It's going to go down really fast. They say as soon as you drive a car off the lot, it loses its value. It loses its initial value. And so it's going to go down really, really fast. P sub 0 here is the initial amount. So if I talk about like the price of a car or how much I invest or something like that, really essentially this formula right here is the continuously compounded formula, right? We already kind of saw this formula being used. This was the PERT formula when we said, what is the amount of money that I would have if it was compounded continuously? So this really is the same formula, but we're using it a little bit different here because our K value could either be positive or negative. When you have like an investment account, that investment account's going to grow over time. So we only talked about it with a positive value. T is time, and time is always in years. So we're going to look at some different scenarios of where we could kind of see and use some of these things today. What I'm going to do is I'm just going to do a couple of examples off of or out of your book today and talk about some of those, because what's going to happen is we're going to have problems today. Probably not going to assign a ton of homework problems today because a lot of them have like multiple parts to them. They have like an A, B, C, and D. You're going to do a lot of different things. We also have kind of a formula today that we call doubling time. And we can use this same formula anytime we want to double something. Okay, so if I wanted to say, if I invested $1,000 and I wanted to figure out how much time would it take for that $1,000 to grow to $2,000, then I would need to know what is the rate of growth, right? If the rate of growth is 2% versus 12%, then it's going to grow at different rates, right? And so at 12%, it's going to grow faster than at 2%, where it's not growing very much. And so if I wanted to figure out what this is going to be, then we're going to take the ln of 2, and we use 2 because it's doubling. If I said tripling, I could use 3, but doubling is the most common one that we're going to see. I could take the ln of 2 and then divide it by k, and that could give me t. That's how much time. Or I could do the ln of 2 divided by t, and that could give me my rate. So you could do it either way. It works either way. If I gave you a rate of, let's say k is 6%, so an account is growing at 6%, and I wanted to know how long will it take that account to double, then all I have to do is take the ln of 2 and divide it by, now here's where you got to be careful. We can't just divide it by 6. We have to divide it by 0.06. Anytime we have a percent, we have to divide it by whatever that k value is. So if I take the ln of 2 and divide it by 0.06, it would take almost 12 years for that account to double. About 11.6 years. Okay. If I said I want my account to double in 4 years, I want it to grow from $1,000 to $2,000, and I want it to be there in 4 years, okay? Then I would take the ln of 2, and I would divide it by 4. So if I do that in my calculator, I get like 0.173. But when we write this as a k value or as a percent, we got to move that decimal over. And so I would need to get a 17% rate in my account, which pretty hard to do. Some years, stock market's better than others, right? Dave Ramsey, personal finance, says 12% is kind of what you would want to try to get. Not all accounts are going to get that, but 17 would be even higher than that. So to get your account to double in 4 years is probably going to be pretty hard to do. Okay, 6 years, probably a little bit more doable. 12 years, we could probably get 6% on something. Okay, so a couple of different instances there where you can figure out how long it takes something to double. All right, if you have your book, you can get it out and kind of follow along. Otherwise, I'm just going to kind of go through some different examples here. We're on page, let's see here. First one we're going to do is number 12. So we're on page 391. Okay, so number 12 is talking about food decay, okay? And decay is kind of the key word here. Decay means that the quality of the food is decreasing exponentially. In a study of the decay of sugars in apples, biologists measured a density of 0.264 on day 0 and a density of 0.075 on day 15. Assume that the density of sugar and the apples decreased according to the potential decay model. Okay, so what we're doing here, I'm going to write out the formula that we did just a second ago. Okay, P sub 0 is what is the amount at time 0, at the very beginning of this data, whatever we're talking about. And so that is 0.264. Okay, we don't know what K is. But in this case, usually time is in years, but in this case it's in days. And so that's the one difference between compound interest and this problem here today is now my time is in days instead of years, but usually it's in years. The ending value is your P of T, and that's 0.75. Okay, so we got to kind of insert, based on the information that we're given, we got to kind of insert the information into our formula. You're using the same formula all day today, okay? And we have to figure out what is our K value. That's the first question. Part A says, what is the K value of this situation, okay? So we got to solve this. And this is where we're going to do kind of the same things that we did yesterday. I want to get K by itself. We saw some problems like this yesterday. When I have a number in front of the E, what would I do to get rid of that 0.264? Divide by it, okay? Because this is assumed to be multiplying by E. So I'm going to divide by 0.264. So I'm going to do 0.075 divided by 0.264. Okay, now here's what I would recommend is leave that number in your calculator because it's like a big long decimal. Don't try to round it. That way you're a little bit more accurate with your number. So leave that number in your calculator. And then we're going to log it, frog it, solve it, like we did yesterday. Okay, I log both sides. I log this number here. I log E. And then I went ahead and put the 15 in front just because we usually have the variable or the number in front of the variable. You can either leave it as 15K or K times 15. We said yesterday that ln of E is really 1. So that gets rid of my ln of E. And then we're going to take both sides and divide it by 15. So we're going to take the ln of that number we just had, and most of you have like a second answer button at the bottom of your calculator. Usually you have to hit second to get there, and I think on a lot of these TI calculators it's above the negative button. I think on Casio's it just says A and S. But you can go ln of that decimal that we just had, leaving that decimal in your calculator, and then divide it by 15. So you might try putting this into your calculator here. I'm going to round it to the nearest thousandth. So we're going to say here about a negative 8% decrease. Okay. Everybody able to get that in their calculator? You might try punching that in just to make sure you know how to put that all in. It's not overly difficult to punch in, but just being able to interpret the answer also is a big thing. Anybody need help with the calculator? Did you get in it, Shaylin? Okay. Okay, so that's part A. Okay, negative 8.4% would be our K value. Part B asks us what would be the amount, estimate the sugar density in the apples 5 days after the experiment and then 18 days after the experiment. So T equals 5, T equals 18. Okay, there's two ways that you could do this. You can either plug it right back into the function. You could put it into the calculator and type it in and then go to your table of values. So here's what your equation is going to look like now. P of t equals and then we're going to use that number. And the first thing we're going to do is we're going to multiply it by 5. Because we're going to do it for 5 days. What would be the value or the amount of that after 5 days? This is all in the exponent. And you could type it in just like this, but make sure you put this exponent in parentheses. So another one, try putting that into your calculator. So the value of that would be about 0.173, depending, it kind of depends on what you round this value to here. Your answer might kind of change a little bit based off of that. Okay, and then we're going to plug in 18. So we do exactly the same thing, except this time we're going to plug 18 back into that equation. So we're going to type this whole thing in, but all I'm going to do is replace the 5 with an 18. Okay, and this one. Okay, so the substance is going down, and that's what this negative value right here is doing, is the amount of that substance, whatever that is it's going down over time, okay? That's why it's important to have a negative number right here. If this was positive, the amount would be going up. And so that's the one thing you got to really watch for today, is what is the value of K? Is if it's growing, it'll be positive. If it's decreasing, it'll be negative, okay? Anybody need help calculator-wise? Everybody able to get those numbers, okay? All right, so that's number 12. That one only had 2 parts to it, pretty straightforward. The other one we're going to do is on the same page. This one is number 14. So the first one was a decrease problem. This one's going to be an increase problem. This one has a few more parts to it. A couple more questions that they're going to ask us. This one is talking about the price of this car. In 2003, this car was sold for $18,045,000. It was originally purchased in 1972 after it had been damaged for only $2,400. Okay, so 1972 it started off at $2,400 and now it's worth over $18 million. Probably would have been a pretty decent purchase, huh? Back in 1972. We're going to put this into a formula. So first of all, I'm going to say P of t equals the initial value is $2,400. Okay, that's where you got to be careful here, because this is the amount that we originally purchased. Original amount, original price, whatever that is. Okay, and they do tell me in part A that V sub 0 is 2,400 though. They're using V instead of P. Don't let that confuse you. They're just using V because it's the value of the car. I'm still going to use P just to keep it consistent. They're going to change things out a little bit. Okay, we want to find the value of K. So now, way down the road, this car is now worth $18,045,000. And it's asking us to find the value of K, kind of like we did just a second ago. But we also know the amount of time. So how much time passed from 1972 to 2023 when they sold it again? 1972 to 2023. 51 years, okay? And so I'm going to go ahead and, I'm just going to write it like this. We don't know the K value. We could say K times 51, but I'm just going to go ahead and write it as 51K because we know the time, we don't know K. I know everything in this problem except for K. So now my goal is to solve for K. And so, like I said, this is really like what we did yesterday, okay? This is basically solving, and it's log it, frog it, solve it. But before I can log it, frog it, solve it, first step is to divide by 2,400. Now, I'm going to show you a little bit of a trick here. I would wait and put things into your calculator until the very end. Okay, then we're going to log it, frog it, solve it. Okay, so what we're going to do now is, and you're going to kind of see that a lot of these problems are going to be very similar in the solving of them. So if we log it, I went ahead and frogged the 51K over in front. We have the ln of E again, like we did on the last problem, which is really 1. And then I'm going to take both sides and divide it by 51. Okay, so I kind of like to just write it all out rather than typing it into my calculator as we go. Now that I have it all written out, we're just going to type this whole thing into my calculator all at once. Because it is kind of a multiple step process. Okay, so if the question said what would be the percent rate, then this would be, this car value increased 17.5% over those 51 years. It's a pretty good increase, but it would make sense because it went from 2,400 to over 18 million. So obviously the rate of increase, and it was over 51 years, so it's increased a lot of time over those 51 years. But when we put it into the formula, we use the 0.175. Okay, this would be the rate of increase. This would be the number that we put into our calculator. All right, so that's part A. Part A was, what is the K value? Part B, estimate the value of the car in 2030. Okay, so in 2030, we now know the K value is 0.175, okay? And once again, you go back to 1972 as our starting year, and if I go from 1972 to 2030, really you just add 7 more to my years, right? In 2023, we had gone 51 years, so in 2030, that's another 7 years down the road. So 7 more years down the road, we would have taken 58 years. And so now we're going to put that into our calculator. When I put 58 in for that function, we're going to try to figure out what the value of the car would be at that point in time. Fairly large number, right? In 2023, it was 18 million, a little over 18 million. So 7 more years down the road, if it keeps increasing in value like that, then 61,418,645. Okay. And you could go to cents here, but going to pennies here probably wouldn't make much difference if if I had a $61 million car, I wouldn't really care too much about how many pennies we got, right? Plus, don't forget that 30 cents, right? I think I would just run with the 61 million. That would be part B. Part C, what is the doubling time? So what did it take for this car to double in value, okay? Because it's doubling, this is the formula I talked about at the very beginning of the lesson. We're going to do the ln of 2. The ln of 2 stays the same every single time. The only time this would change is if I was doing tripling or 4 times or 5 times. But doubling is the one we do the most. How much time does it take for me to double? And K, and we know that K is 0.175, so we're going to move that down here, and we're going to divide by 0.175. So if I do the ln of 2 divided by our K value, it's going to double every almost 4 years, about 3.96 years. Okay. And that would kind of make sense here too, because in 2023, it was 18 million. If I doubled it 4 years down the road, it would be now 36 million. And 7 years down the road, it was worth 61 million. So that would just kind of make sure your answer kind of makes sense with what's going on. Okay, and then the last question here. How long will it take that car value to reach 50 million? Okay, well, we know in 58 years it reached 61 million, so it's going to be less than 58, but we want to figure out about how many years would it reach that. And so what we're going to do is we're going to plug in 50 million as our ending value and set it equal to the formula. The only thing we do not know right here is we don't know how many years, right? We're trying to figure out T. So very, very similar to the process. Now, because I told you that a lot of these are the same thing over and over and over again, okay? You're going to be doing the same process on these types of problems over and over and over again. What you're really going to be doing here is you're going to take 50 million divided by 2,400. You're going to take the ln of that divided by 0.175, and that's going to give me my T. So what did I do? Well, I logged it, frogged it, solved it. I just kind of shortened the process, right? I divided both sides by 2,400, and then I logged it, and then I divided by 0.175. I'm just trying to show you that you can shorten the process down because it's the same thing over and over again. Sometimes we're dividing by K, sometimes we're dividing by T. Like up here, we divided by 51 because it was the number of years. Here, I'm dividing by K because K value is what we know, and I'm trying to figure out how much time is it going to take. That's why this right here, when I do the ln of 2, just means the price is doubled. So like originally, the first time we did it, like if it doubled to 4,800, then my number would just be 2. So how long did it take to get there? So that's why ln of 2, or doubling time, works. Okay, so if we put that whole thing into our calculator, we get about 56.8 years. A little bit less than the 60 million we had, and because this one only reaches 50 million. Okay. So a lot of different questions that could be asked here. You can find time, you can find K, you could find out how long does it take to double. There's a bunch of different things that go into it. All of these problems are essentially the same thing, just doing different things with them. Good thing is it's the same formula over and over again. Okay, homework for today. 389, 392, 7, 13, 15, 16. And they're all going to be essentially the same thing we just did. Different number of parts on each one. I'm going to kind of walk you through number 7 a little bit here. Show you kind of a shortcut. We didn't really talk about this yet. So then the first one will be about done with by the time I get done with this one here. Suppose that you invested $10,000 at an interest rate of 5.4% compounded continuously. So this is really just our PERT formula. And if you wanted to use the PERT formula, you could do that. Okay? The PERT formula and the formula that we're doing today is the same thing. It says compounded continuously, but today we are using P of t equals P sub 0 E, and then we're earning 5.4%. Just make sure you change that to a decimal. That's the big part. And then t. Okay? So part A just says, write an exponential function that describes the situation. That's my equation. Part A is done. Okay? Now, for part B, it wants to know how much would I have in the account after 1 year, 2 years, 5 years, and 10 years. Because I have to do 4 different values here, then for me, I think the easiest way to do that is just go to my calculator, okay? And what I would do then